Okay, so from today, we will learn about the visual language models. So recently there has been some approaches that try to combine the language signals with the computer vision signals. So we will learn about that, okay? So most of you already heard about the GPT, okay? So nowadays we are using ChatGPT, okay? So GPT is, how to say, the foundation model that can be applied to many downstream tasks. And ChatGPT that is the model applied for the chat application. So nowadays we have foundation models, which is trained using large-scale data in the unsupervised way or the self-supervised way. And we are using these foundation models into many downstream tasks. Okay, so downstream application, maybe, yeah. So ChatGPT is one of the kind of downstream application, okay, that uses the GPT, okay, and also the GPT, that's the abbreviation for generative pre-trained transformer, okay. And this GPT-1 is published in 2018, okay. So this is using the transformer architecture, especially the decoder architecture. So we first train the transformer for using the, how to say, text data, okay? And we train that in the unsupervised way. And then using that foundation model, we apply that into many downstream tasks. So downstream tasks are, for example, classification and similarity measure and multiple choice Q&A, maybe. So in natural language processing, we did this type of things using the foundation model whose name is GPT. So first, we have to pre-train the foundation model using unlabeled large-scale data. So what they do is actually doing this. So you can interpret this as the word in the sentence. So for example, I am a student, okay? Then this is U1, U2, U3, U4. Each word that is denoted by this symbol U, okay? So the task we do when training the GPT, when doing the pre-training the GPT is, we predict the next word given previous word, okay? This is the GPT's parameter, and this is the given previous word in the sentence. And then we estimate the next word in the sentence, okay? So there does not need any labels have to be created for this kind of task. So we call this as the unsupervised or self-supervised training, okay? So the sentence itself have supervisions, okay? Even though we don't give any labels for this sentence, naturally, given these three words, we can predict the next word, okay? So GPT tend to understand the relationship between words, okay? So this is the pre-training happening in the GPT. And also the next step is we fine-tune the foundation model that is unsupervisedly trained using the sentence data. We now fine-tune the GPT architecture, which is pre-trained to the downstream tasks using their corresponding labels, okay? Corresponding ground truths, okay? That's the fine-tuning stage, okay? So there are many downstream tasks in the NLP domain, natural language processing domain. So, okay, for example, there are many available data sets for that. Okay, so I mean, what they want, what they say is, okay. Anyways, what they wanting to say is, compared to the LSTM, the transformer-based architecture, they are producing better accuracy in many downstream tasks. And this is the average score for downstream tasks, okay? So, and the next lesson we can learn is, if we pre-train the transformer, which is the step for making the foundation model, I mean, the average score for downstream tasks, they are becoming better, okay? So this is the reason why we wanting to have the foundation model, which is unsupervisedly pre-trained, okay? So by comparing these two laws, you can see that this pre-training with large-scale unsupervised learning is effective, and also the transformer architecture that's better compared to the LSTM competitive alternatives. Okay, so this is the first GPT that is proposed by OpenAI. Okay, so nowadays we are having GPT-4, so they are scaling up this GPT-1 to have more parameters compared to the GPT-1. Okay, so I will explain that later. But there have been in between GPT-1 and GPT-2, there have been both, okay, BERT, there have been both. And GPT-1, GPT series was proposed by OpenAI, and BERT that's proposed by Google. So actually they are competing each other to, I mean, conquer the NLP domain, okay? And what they do is actually similar to what GPT is doing. And also you have to see their BERT is abbreviation for bidirectional encoder representation from transformer. Okay, so actually BERT, that's also using transformer architecture, but they are mainly using the encoder architecture. Okay, so they are stacking multiple transformers encoder architecture to pre-train the text signals and also fine-tune those foundation model for multiple downstream NLP tasks. Okay, and this BERT is proposed in the year of 2019. Okay? And what this is also done with the two steps. First, we pre-train this BERT architecture, and second, we fine-tune this this foundation model for downstream tasks. And this is showing which kind of pre-training was done. Again, the pre-training is divided into two tasks. The first one is masked language model, and the second is the next sentence prediction. This is similar to GPT, but this is somehow different. So actually, given text data, we have multiple sentences in our data, okay? So, okay. So this is the token for, saying that the starting token, okay? And this is token for indicating the sentences end, okay? And there are actually two paragraphs here, okay? So the first task for pre-training the BERT is we on purpose make a mask, okay, in each sentence. So on purpose, we delete this word, okay, and try to reconstruct this word given other words as the context. Okay, so this is similar to what we have learned for context encoder in image domain. Okay, so we on purpose we remove this patch, and given the patches around this patch, we try to reconstruct these images. That's the context encoder. Similar to that, we on purpose remove some of the words in the sentence and try to reconstruct that using other words as the context. That's the first task, first pre-trained task in BERT, mask language modeling. So we randomly generate mask for a particular word and try to reconstruct that. That's the unlabeled data, but we can make the supervision using the original word. Okay? And the second task here is next sentence prediction. So this is, for example, the label. Okay. So this is one. This is one data, and this is the other data. So this is the data number one, and this is data number two. So there are, there's no relationship between these two. They are independent, but this is two sentences given for one data. So, and we have label for this, whether these two sentences are sequential or not. Okay, so in the original data, in the original paragraph text data, we can know these two sentences are originally in the sequence or not. Okay, if they are in the sequence, we label it as is next. So it is indicating that this sentence is next to this sentence. Okay, but if in the original paragraph, if these two sentences are not sequential, then we label that as not next. Okay, so it is indicating that this sentence was not originally next to this sentence. Okay, so using this label, which indicates next sentence, okay, we can do the second task. Okay, whether these two sentences are sequential or not. That's predicting that is the next sentence prediction task. Okay, so the first task is we randomly generate masks inside the sentences and try to reconstruct that word. Okay, that's the first task to pre-train the BERT. And the next is the next sentence prediction, whether these two sentences are sequential or not. Okay. So this is the pre-training stage. So we pre-train BERT, which is the text of the transformer encoder, using many unlabeled sentence data. Okay, using these two types of tasks, we pre-train the foundation model, and then we fine-tune those pre-trained foundation model BERT to many NLP downstream tasks. Okay, that's the BERT. So actually, that is actually composed of two steps. We pre-train BERT, the foundation model, using many unlabeled data via self-supervision, and fine-tuning is required to test it for each task. Okay. And this is some result for BERT. So this is indicating different backbones. So if we stack more layers in BERT, then the performance becomes better. Okay, and we can compare the performance of the BERT using the human expert. So it shows that the performance is almost similar to human expert. Okay, and this is the GPT-1. Okay, so after GPT-1 made by OpenAI, the Google proposed this BERT and showed that their performance could be better than OpenAI's GPT. Okay, and this is also previous models. Okay. And after BERT, this is the number of parameters. GPT-1 have this number of parameters. BERT, they are using this number of parameters. And GPT-2 have more parameters than BERT and GPT-1. And GPT-3, that is also having more parameters, okay? So gradually, the OpenAI, they are wanting to scaling up their foundation models. And in the year of 2020, they publicized the GPT-3 in Europe's conference, and they are saying that by scaling up the language models, we can make some few-shot learners. Few-shot learners means normally we need many trained data to make the model perform well for the testing data, right? But what few-shot means is for specific classes, for example, let's say this is the classification task, okay? Then, let's say there are 100 classes, okay? Then we need many training data, which is balanced for each class and having enough samples for 100 classes to make it work for testing data, which have 100 class, okay? But let's say we wanting to expand the model's capability to classify the new 101st class, okay? And we will give it just maybe 5 samples for this class. Okay, for 101st sample, we will give very few samples and wanting to make it work for this new class. Okay, in this situation, it is called as few-shot learning case. Very few shot was given as the training data, so we call this as the few-shot learning. Okay. Sometimes we call it as one-shot learning if we give instead of these 5 samples, if we give just 1 sample for each class, then we call it as the one-shot learning. Sometimes we give 0 samples for this new class data, but wanting to achieve the classification for new class, then that case, we call that as the 0-shot learning, okay? So subsequently, we will see this type of terms. So I'm explaining that, okay? So few-shot normally is less than 10 samples for each class, but of course, the performance for these few-shot classes are reduced compared to the original class, okay? But making it less, the performance lessening the performance dropping is the objective of this few-shot learning. And also one-shot learning, even compared to the few-shot learning, it is harder to maintain the original performance and at the same time the new classes performance, but making it less compared to other algorithms is the objective of this one-shot learning. Also similar to zero-shot learning, even without giving any training samples for the new class, they are wanting to achieve comparable performance to the original baseline classes. So that's the objective of the zero-shot learning. Anyways, this is the several variants in GPT-3. So they are providing multiple architecture in GPT-3. Especially, this is the largest model, and we are calling this as actually the GPT-3 model, okay? Having very many parameters compared to the previous foundation models, okay? And actually, you can see this is the final GPT-3 model, okay? And this is the GPT-3 small, having less number of parameters. And this is the GPT-3 13 billion model, okay? So this is the number of data samples, okay? Number of data. And this is the accuracy. So as number of parameters are increased, their accuracy becomes better. But if we maintain the architecture very big, have the many parameters, then their performance, the speed of performance improvement is dramatic compared to the small scale GPT-3 models, okay? So that's the lesson here, okay? So, I mean, scaling up the architecture size, that's very helpful for making the accuracy becoming better, okay? And this is showing the zero shot case. So here, the data, number of data is not provided. So that is actually showing the zero shot case, okay? And also one shot case, okay? Even one samples are given to GPT-3, their performance for one-shot learning is becoming a lot better than small-scale GPT-3 architecture, okay? And zero-shot, they are similar, actually. But even in this case, the bigger models, their performance is better than smaller models, right? And here, their gaps are becoming dramatic. And even few shot cases, there are a lot of differences, okay? Depending on their size of the architecture, it is becoming better, okay? Especially in the few shot cases. I mean, when we are given with many data, then it will be, maybe this model's performance might be becoming similar to the large scale model, right? But our data set is not complete, okay? In some classes or some, some samples in training data, we cannot have complete training data. So this kind of fusion learning capability is very important in large scale models, okay? So by not explicitly giving specific samples for explaining some classes, this GPT-3 can be generalized to those new samples without seeing any, training samples, okay? So to do that, their lesson from this paper is we can scale up the language models, okay? So yeah, this title is saying a lot of things, okay? And this is showing how the training data have been constituted, okay? So they are using multiple NLP data to train this GPT-3. And this is the result using the GPT-3, okay? So compared to the state of the art for individual downstream tasks, the GPT-3, their zero shot, one shot, few shot capability already becoming better than some of the downstream tasks and comparable to some of the other downstream tasks, okay? So without training with many data, without seeing many data for specific tasks, they already get very good performance, okay, with the zero shot learning, okay? And if they see small samples for specific downstream tasks, then it can be better, actually. The performance could be improved. And without without training specific downstream task-specific models, they can achieve comparable performance. That's the merit of GPT-3. Okay. So you can go to here for GPT-3, and now we are having GPT-4. Okay, and 4O actually. 4O means omni, and means multi-modality. Okay, GPT-3, till GPT-3, we use only the text signals, but GPT-4O, they are using even images and others. Okay, image and speech. Okay, they are using multimodal signals, so that is the reason why they have O here. And actually, these VLMs, they are expanding more and more. Okay, but we may have to some of the more specific examples that starts to align the text signals with the image signals. Okay. Actually, one of the representative work for this type of work is CLIP. Okay, so CLIP is also proposed by OpenAI. Okay, this is also very important work. Okay, their purpose is they want to align the image feature and the text feature. Okay. And by doing that, you can feel like that some of the generalization capability, especially one-shot, zero-shot, few-shot learning capability is improved. So you will see when explaining this part. Okay. So this is the merit of aligning the text and image signals. Okay. So first, to achieve that, we first have to pre-train the image encoder and text encoder. So encoder normally means extracting some feature, okay, from the image or text. So text encoder extract features from the text input, okay, and image from the images, image encoder extract the features, image features, okay. So we are training this text encoder and image encoder, okay. That's called as this kind of contrastive pre-training. So contrastive pre-training is called as contrastive because of this step. Okay, so actually you can see we already know the image I, their corresponding text description is T1. Okay, for first sample, the image is I1, and the corresponding text signal that is T1. Okay, so for I1, if we dot product these two features, this I1 is denoting the image feature for the first sample, and this T1 is denoting the text feature for the first sample. Okay, and this is showing that we are dot producting these two vectors. Okay, if we product these two vectors, okay, then it is measuring the similarity of these two vectors. So if this I1 and T1 shares, they are becoming same, then this value will become larger, okay, unless they will become less, okay. And here, T2 is denoting the text feature for second text, okay. For example, here, it is denoting the nth samples text feature, okay. And you can see in the first row, we are dot producting the image, first samples image feature with all other text features, okay? And we have to enforce this is becoming the largest and suppressing all the other terms, okay? Because I1 and T1, they are corresponding image and text signals, okay? We have to make this larger than others, and we have to suppress other dot products, other similarities, okay? And also the other thing is, if you see in this direction, this T1 is in this, in this part, you can see T1 is dot producted with multiple image features, okay? But these have to be largest because I1 and T1 are aligned, or others are, not paired, okay? So these have to be largest in this direction and this direction, okay? So, and also for this line, these have to be the largest, and for this line, these have to be largest, and so on. These have to be, only the terms in the diagonals have to be largest and suppressing all others, okay? So because of this, they are called as contrastive learning, and because we are pre-training these text and image encoders, and we call that as pre-training, okay? In this contrastive learning, we are aligning images with their corresponding text signals. So their learning is actually aligning the text and image signals, okay? This is the pre-training stage. And using many data, the image and text pairs, if we do this type of contrastive learning, then the thing we can obtain is, for given images, if we extract features for these images, then, and also if we extract features for text signals, that text inputs that describe these images, then their features are becoming similar. Of course, they are in the same dimension, but their feature values, their elements becomes similar when the text is describing the same object inside the image, then their feature responses are becoming similar, okay? That's the, this contrastive learning is insisting, okay? And if we do that, the interesting characteristic we can obtain is this part. So actually, you can see we can do zero-shot prediction in the image classification. So, when achieving the image classification, we already learned about that. So we normally use some architectures, CNN architectures like ResNet, to classify images. So given this image, we apply CNN and we apply cross entropy loss to train this ResNet. And at the end, we have the n-dimensional class probability. And by doing argmaxing, we are choosing one element, okay, and choose that as the, predicted classes, okay. The element that have the largest value in the n-dimensional, last n-dimensional vector, that is actually chosen as the, as the class we are predicting, okay. So this is the classical image classification task, okay. But if we have 100 vector, okay, during the training, but if we want to classify 100 first class, which is new to this model, then we cannot actually do that in this kind of fixed dimensional output. We cannot achieve classification for 101st, which is the new class. Okay, this is not trivial in classical image classification network. But using this CLIP foundation model, we can achieve it easily, okay? Because, so I will show how we can achieve this zero-shot prediction. So for the input images, so I mean, during the training, we are of course using many labeled paired image and text data, but at the testing, there could be new class samples which is not seen during the training. Okay. Anyways, for that image, we will extract the image features here. Okay. And we will also extract the text features. Okay. Here. Okay. Using n number of text. Okay. Using n number of text. We will extract using pre-trained text encoder. We will extract their text features, okay? And then we will dot product this image feature with all other text feature, and then choose one dimension, one element which have the largest similarity. And actually, we will choose that text as the class label, okay? So even though we don't have this images class during the do is we can add 100 first new class name here and choose, I mean, have extract their n+1 new text feature and compare it with I1, which is the image features of this input image. And if it has the largest similarity, then we can simply choose that, okay? So because of this characteristic, this zero-shot prediction is becoming very simple in this CLIP paradigm, okay? Are you guys following this? So this is CLIP. So, and also this is highlighting the CLIP pre-training. So in this direction, this is the corresponding image and text signals. So if we apply softmax in this dimension, these have to be maximized, okay? And also in this direction, this is the corresponding matches between image and text. So by applying softmax, these signals have to be maximized and all others have to be minimized, okay? So actually here, you can see that. So we have two directions in our final logit, okay? So logit is meaning this kind of thing, okay? The final output that is called as logit, the dot product between this, image feature and text feature that is called as logit. And using their, we already know which index have to be maximized. That label is indicated here, okay? So we are actually applying softmax and applying cross entropy loss in two directions, in this direction and this direction, okay? And by averaging those losses, we are training the overall CLIP, the image and text encoders, okay? That's the CLIP training, okay? And they are training, during training in this part, we have to secure the aligned text and image pairs, okay? So this CLIP, they secure this amount of large scale image and text pairs from the web, okay? And also they provide two types of architecture. One is the ResNet-based, which is the CNN-based, and the other one is the VIT-based image encoder, which is the transformer-based encoder. And they are providing only one architecture for text encoder. So image encoder, they are providing two architecture, which is the CNN-based and transformer-based. And for the text encoder, they are providing the transformer-based text encoder, okay? So what I'm saying is, this is a transformer-based architecture. And for the image encoder, they are providing two types of architecture, which is ResNet-based and VIT-based. Okay, so in their webpage, they are providing the pre-trained text and image encoders using the contrastive pre-training. Okay, and the interesting characteristic of this clip architecture is this brown star is they are denoting the clip architecture, and showing this type of various colors, they are denoting different normal CNN or VIT architectures. And this is the ImageNet score, which means pre-trained by ImageNet and testing on the ImageNet. But this is denoting pre-training, training on the ImageNet and transfer to other data. Okay, that's this performance. And this performance is ImageNet pre-trained, in benchmark test result. And this is the transferred testing result. The clip is showing very good generalization capability, but for other architecture, which is using just cross-entropy laws, they are showing very limited generalization capability. In benchmark, their performance is good, but for the transfer tasks, their performance is becoming less. Okay, and this is showing the speed. Okay, and compared to depending on the speed, they are showing the average score. And if it goes this direction, that is denoting fast and good algorithm. And this is the clip. So speed is also very fast in clip. Sorry. And this is also very interesting graph. So they are showing multiple benchmark, image classification benchmark, okay? And this green is denoting that for the Stanford CARS data set, zero-shot clip means they are pre-training clip using 400 million image and text pairs obtained from the web, and they haven't fine-tuned the clip on this Stanford CARS data. But they are saying that the clip's performance is better than ResNet 50 architecture, which is especially trained on this data. And the clip is almost 30% better than the ResNet architecture, okay? So even without fine-tuning, the clip is showing very good generalization capability. So almost half of available image classification data without any fine-tuning, the clip is better than ResNet 50, which is especially trained on this data. And for other data, the clip is less than ResNet 50, which is trained on this specific data, but still clip is very good, very comparable. Even without fine-tuning, their performance is very good, okay? And also this is showing that the few-shot learning and one-shot learning and few-shot learning capability, number of labeled training examples per class. Okay, so this means there was no labeled data, and this is showing one-shot learning case, and so on. So the clip, their performance is very good, actually, compared to other architectures. okay, which is pre-trained on the ImageNet. And zero-shot clip, their performance lies here. Okay. So zero-shot capability of clip is very good, actually. And also, this is also interesting lesson. I mean, this is the ImageNet pre-trained ResNet 101 architecture's performance. Okay. So if this is the original ImageNet data having the real images, okay. This is the original ImageNet data having this type of various object inside. But if we slightly change their styles, even into cartoons, the ResNet architecture's performance greatly dropped. Okay, and even if we transform the original images in the ImageNet into sketch style images, their ResNet performance greatly reduced. However, the zero-shot clip, their performance is almost retained. Okay, so compared to the ResNet, which is once the state-of-the-art model, even you already see that in the year of 2015, ResNet recorded, actually they surpassed the human capability in image classification. But if their input images are having different styles, they are suffering. Okay, but Clip is solving that kind of problem. Okay. And this is some of the weaknesses and strengths of this clip. Okay, so they are very good zero-shot capability, but sometimes their performance is below the state of the art. Okay, this is actually weakness, but still comparable. Okay, so I mean, it anyways works, but sometimes it is less competitive to the model which is fine-tuned on the data domain. Okay, and it is weak in some tasks like counting. Okay, and sometimes their generalization capability is limited, and this kind of text they are I mean weak. Okay, and there could be social bias. Okay, this is clip and their weaknesses, but still they are showing very promising solution for this kind of one shot, zero shot, and future learnings. Okay, and also one of the problem in clip is they cannot be used in the object detection task. So there have been region clip actually. They try to expand the approach of clip towards the object detection task. Okay, clip is more about the image classification. So they are assuming that images are composed of one main object. Okay, but region clip, they are trying to solve the problem. I mean, the strong assumption of the image classification and try to align the region features with the text. So they are doing region text matching instead of the image text matching as in clip. Okay. So their approach is quite intuitive. This is the clip. They are training the language model and the visual encoder. Okay. But now they are having new visual encoder which encode image regions instead. Instead of the whole image, they are encoding each object bounding boxes features. Okay, and also given this text prompt, which describes the image whole image. They are aligning these whole image descriptions with the whole image features before in clip. But for achieving this region clip, they are extracting the object, specific object from the whole image And at the same time, they are extracting the region descriptions. So, for example, in this boy is flying a kite, they are extracting boy and kite, bus and people, okay? They are extracting some nouns from this description and align these nouns with the region features, okay? This is done in pre-training step. And during the testing, they are using the object proposals, which is a selective search. They are using selective search algorithm that can, probable bounding box that can generate probable bounding boxes that have the object inside and apply their region features with the region description and find the most probable bounding boxes, okay? So this is the region clip. They are actually extending the original clip towards the object detection domain. And by doing that, the clip may miss this kind of object. So they are saying that this is subboard, which is incorrect. But in the region clip, they can rebuild that as the umbrella class correctly. And for example, here they are saying this is Thai, but the correct one is person, okay? And this is not skateboard, but the region clip can correctly classify it, okay? So anyways, this region clip, they are extending clip towards the object detection task, okay? And this is another successful and failure cases of the region clip. And another important work is the grounding Dino. Okay, Dino is, I actually missed the Dino, but I mean, this is very recent work published in maybe ICLR 24. And this is actually the state-of-the-art architecture that extends the DETR, which is the transformer-based object detection pipeline. We already learned about that, okay? So they actually improve some of the training method and some of the inference method and make the Dino. The overall architecture actually have the same philosophy with the DTR, but they improve some of the aspects of the DTR training and inference. So they made the Dino. And this grounding Dino is actually marrying this Dino with, grounded pre-training, which is the text, giving some understanding, the capability of understanding text, okay? So they can achieve the open set object detection, which is similar, this term is actually similar to zero shot, okay? Without seeing specific samples during the training, they can be generalized, okay? Thanks to the text, okay? So I will show the example here. So this is the figure 1 of their paper. And what they say is, this is the original object detection task, which is the closed set, having the closed set settings. So, this is the person's bounding box, okay? So person's bounding box. So in the original object detection, we are doing that, okay? We detect object using the same class name which was seen during the training. And this is bench. So bench is here. Okay, this is the original, how to say, or closed set object detection task. But this is the open set object detection task. So the classes are zero shot. Okay, for example, here the class is World Cup. Okay, this is not seen during the training. Okay, and this is year of lion. And how to say, lion, maybe lion or bench was not contained in the training data, maybe, I'm not sure. Anyways, the new, the class can be like this, year or World Cup. That's the new class, okay? But here, it becomes more noble. So the left lion, their class becomes like this. So not merely to the lion, the class name is now becoming the left lion. So because there are 3 lions, among these 3 lions, the object detector had to detect this left lion. Okay, this is actually the noble class. Okay, and here the text descriptions are becoming complicated. So the bottom man with his head up. Okay, so here they are detecting the bottom man with his head up. Okay, this is the noble class. Okay, this is the example of open set object detection compared to the closed set object detection. Okay, so I mean, they are combining Dino with this kind of text interpretable capability and to achieve this kind of noble object detection, open set object detection task. Okay. And here they are showing some method that can give the text interpretable capability. So basically, this is the model architecture. Okay, so they are having 2 streams. This is the image stream, and this is the text stream, and they actually combine these 2 types of features. Okay, so this is the input text, and this is the input image. And they have the image backbones, which is the feature extractor, and also have the text backbones that can extract features for input text. Okay, and they combine this text feature and image feature using this feature encoder. Okay, and regenerate image feature and text feature. This is the enhanced image feature and enhanced text feature. Okay, and at the last step, and also they improve this image feature and text feature, and also compare them similar to the how to say clip. So here they have many text words, and here they are having many image patches, and they are actually comparing their similarity, similar to the clip. And they, by matching this, they are, labeling their, noble classes. Okay, so this is similar to clip. Okay, but they are actually revealing noble classes by matching their feature similarity. And this is the localization part. Okay, so the overall pipeline is basically based on the Dino, which is the state-of-the-art object detector, but additionally, they are having text stream that can compare the image features with their features, okay, and to give more generalization capability. And here they are, detail this feature enhancer, okay, and also for the decoder, they are also combining some of the text signals in the middle, and here they are detailing those decoder part. Okay, so in the middle, after enhancing the text, they are also apply cross attention to this text and image signal to enhance the image features, and then they compare it with the many image patches and text word at the last part. Okay, so this is the grounding Dino. Okay, to give some alignment with text and images, they are proposing this kind of architecture. Okay, and thereby they can achieve generalization. And from here, we will review it maybe this Wednesday. Okay, so there are other types of foundation models. Segment anything, we call that as SAM nowadays, and they are providing very good capability for image segmentation task. Okay, we will learn about that, how they can achieve that. And also there have been LangSAM, even SAM is also using some of the basic text prompt, but they are further extending SAM towards embedding some language descriptions. That's called as LangSAM. Okay, and also we will briefly see this kind of image generation, text to image generation pipelines. Okay, so this DALL-E was the sensational work proposed by OpenAI. Starting from here, we will review the stable diffusion and recent version of DALL-E's. Okay, so that's the remaining part. Okay, so today we can stop here and see you this Wednesday. Okay, thank you.